I want to talk to you about light. Light is something we all think we know about, but there are still many mysteries contained in it. We think we know about it because it's so central to our lives. We receive most of the information about the world through our eyes. And indeed, in the English language, to say, I see, is also to say, I understand. But if we broaden our horizons from the narrow spectrum that we call light into electromagnetism generally, then we see many other things as well. Cell phones, you probably have a cell phone on you, radar, X-rays, MRI, many applications of electromagnetism are very central to science today. And I want to tell you about some new work which we've been pursuing over the last decade or so in London, and particularly at Duke University, where my collaborator David Smith works, onto new materials for controlling light and electromagnetism. These are called metamaterials, and they're important because if you want to make a device or manipulate light in any way, you have to make that device out of something, and that something is a material. And it turns out that in electromagnetism, there's a great shortage of materials. There are many instances where you might just say, I want a material that responds in this way to light, and it's not there. So that's the first thing, to have new materials, which we are generating. And also, if you have new materials, you want some new theoretical technology to learn how to design them and how to control them. And this technology has to be very transparent, so you can use it as a tool to wield it as a sword rather than lift it as a burden, as was once said of Newton. So what is light? Light is a dance. It's a dance between an electric and a magnetic field, one turning into the other alternately. And the step of the dance is what we call the wavelength, and the beat of the dance is the frequency, or in terms of light, the color of light, if you wish. Now, to illustrate the challenges before us, I'm going to set a grand challenge that we set ourselves some years ago to demonstrate the power of these materials and our design technology. You have to sort of do something that's really surprising if you're going to get your ideas through to the general public. So the challenge is to make something invisible, and that would surprise people. It did surprise people very much, and it really told our story to the world. It's not the ultimate thing you can do with these things, but it is the surprising thing and the difficult thing. Now, if you want to make something invisible, the first thing you have to know is that black is not enough. That's conventional stealth. But as you can see from this picture here, that if something's black, you still know it's there because it has a shadow. And here's Peter Pan. It's his statue in Kensington Gardens, just north of my college. And Peter Pan is the little boy who lost his shadow. And when he's lost his shadow, then he's invisible. And that's what we want to do. So how do we set about this? Well, imagine another situation. Say you have a rock in a stream, and the stream is flowing past the rock, and what water does naturally is to part and flow either side of the rock smoothly, so that downstream, if you looked at the surface of the water, it would still look calm and free-flowing. You would not be aware downstream that there's a rock in the river because the water has flowed so smoothly around the rock. Now, light doesn't do that naturally, but I want to show you that using metamaterials and transformation optics, the design technology, we can actually make light flow like water. But we're going to need some help. And who better to call on than this man? And actually, it was one of the key experiments that showed that Einstein's general theory was right, that he predicted that because of the sun's gravitational field, which distorted space, then if you viewed a star which was about to be eclipsed by the sun, and you can only do this at an eclipse, of course, then the light from the star would appear to come from a different direction of the sky because the light was being bent around the sun. And that was a hugely controversial prediction at the time because Newton said that gravity acted between massive objects, and Einstein said, well, it does, but it also, because it bends space and light moves in that space, it will also affect how light propagates. And since those days, more sensational instances of the bending of light by gravitational fields has come to be seen. So this is a picture from the Hubble of two galaxies. The red one is in the foreground, and it's very, very massive. And behind it is a blue galaxy, and the light is flowing around this red galaxy bent by the intense gravitational fields that galaxy produces. So in Einstein's theory, light can flow. It isn't quite flowing smoothly around and closing up. But this gives us a clue to what we have to do. Now, the materials available to us at the moment are things like glass, which certainly changes the direction of light, but it does so at an interface. There are these sharp changes, and that's not what we need to happen. We want a smooth flow of light. And this is where we come to say what metamaterials are. So with ordinary materials, like glass, if you want to change the properties of glass to make it more refracting, so you can make, say, a nice wine glass out of it, you add some lead, and that makes it more refracting. And by changing the chemistry, you can change the properties of the glass, which are due to the constituent atoms and molecules, of course. But a little while ago, we recognized that those constituents of the material didn't have to be as small as an atom or a molecule. They could be somewhat bigger, big enough that with nanotechnology, you could actually make them, and mechanical things. So you could alter the property of a material by changing its structure rather than changing its chemistry. In practice, of course, we use both. I'll give you a nice example of how changing the structure changes the property of a material. If you take silver, a flat piece of silver, well polished, is a very, very good mirror. It's one of the best we have. But if you take that same silver and grind it in very, very tiny nanoparticles, a few nanometers across, into silver colloid, then it's perfectly black, one of the blackest substances known in optics. And you've probably seen that because if you look at an old-fashioned black and white photographic negative, the black is colloidal silver. And so we haven't changed the chemistry, we've just changed the structure, and you get this very, very radical change in properties. Now, in fact, although I've talked about this in terms of visible light, the technology applies over the entire spectrum. And as you may imagine, at longer wavelengths, and these structures have to be much smaller than the wavelength to work properly, at longer wavelengths like radar wavelengths, which are 10 centimeters, the structures don't have to be nanometers across, they can be millimeters across, and that's where the technology was first proven. So here's one of the first metamaterials made by Mike Wiltshire at a time when I was consulting with Marconi, where all these ideas were born. And what we have here are copper rings, which are a few millimeters across, and they're designed to interact with radar waves with a wavelength of about 10 centimeters. And the idea here was to produce magnetism without magnets. So if you put some radiation on here, the magnetic field of the radiation will induce a current flowing around the copper ring. And then in turn, a current flowing in a ring will itself produce its own magnetism. So you get a magnetic response from this structure, which is just made out of copper with no intrinsically magnetic materials there, and that's proved quite useful in manipulating radar waves. Here's another structure. This was made at UCSD by David Smith and his team, and they exploited these magnetic structures and also the little copper wire here which fiddles with the electrical bit. And they, for the first time, using metamaterials, produced a material which is not known in nature. And this is a material which exhibits something called a negative refractive index. It bends light the wrong way when it enters that material. More about that later if I have time. And again, going down in scale, in Zhang Zhang's group at Berkeley, they're making metamaterials for negative refraction on the nanoscale. So here, in this case, is 1 micron, and this is the so-called fishnet structure made from layers of silver and magnesium fluoride. And this fishnet structure exhibits negative refraction. So that's a little overview of what metamaterials are. What are we going to do to specify what metamaterial we're going to use to make a cloak? So here we have to turn to Maxwell, and he produced equations which are exact for all the properties that we're going to consider today. And he was the first person to realize that light actually was this dance between electricity and magnetism. Now, there is, in my view, a problem with these equations as a design tool. If you put them in the computer and ask the computer a question, it will answer it very precisely. But I challenge you to stare at those equations and tell me how, in which direction light will refract at a surface. So they're not very intuitive. Even to people of a very mathematical bent, they're not very intuitive. So what we want to replace them with is a reformulation of Maxwell's equations, which we call transformation optics, and it's going to replace the old optics, which has survived to this day, things like Snell's law, which don't know anything about the wave nature of light, don't know that light can reflect at a surface as well as refract, but has been used for many years, even past the invention of Maxwell's equations, because it is so intuitive and enables you to design things and invent things. And we're going to move to this new vision, and the entities we're going to manipulate here are not rays of light, but the entities which appear in Maxwell's equations, which are the electric and magnetic fields. So back to Einstein, because what Einstein showed was that this effect of bending light was due to the fact that the geometry of space is altered. And he described the geometry of space with something he called the metric. And the metric describes how much space is squashed or stretched or pulled. And it's a quantity called G, the metric. G for gravity, I suppose. And what he also showed was that when he rewrote Maxwell's equations, Maxwell was Einstein's great hero, by the way. He had his picture over his fireplace in Princeton. And when he rewrote Maxwell's equations, taking account of this distorted geometry, what he found was that the metric, G, comes in exactly the same place in the equations as does the refractive index. So it's no surprise that the sun is bending light, because it is, in fact, as far as light is concerned, a lens. And so what we're going to do is to take some light, and here's one of the magnetic or electric field lines of light as it goes through space. We don't want the field line to go in this direction. So if we could manipulate space, we could distort space as if it was a rubber sheet. That's Einstein's idea. And then the field line behaves as though it's nailed to that or glued to that rubber sheet. So as you pull the rubber sheet, the field line remains attached to these points of the sheet, and you can distort its trajectory that way. Now, thanks to Einstein's insight, we don't need a black hole or whatever to distort this trajectory in this way, we can actually do it using a refractive index. And so by exploiting this idea, we can have an intuitive way of how to design things. And its most beautiful application, to my mind, is in the design of the cloak. So here's what we're going to do. So this is what the light would do. It would pass through this region here in which we want to hide something. So inside this circle, I want to hide something. So the light mustn't pass through that circle. Rule 1. Rule 2 is that an observer sitting here must see exactly the same as they would see if we hadn't done any fooling around here. So it's the rock in the stream and the flowing of water. We want to make the light flow around this obstacle, but not be deflected here. Now, just for a moment, think how you would write some computer code to do that, knowing only Maxwell's equations themselves. It's a very difficult challenge because you'd start off by saying, yes, the light must avoid this thing, so let's push it this way. But somehow in your calculation, you've got to remember exactly which direction it entered here so that you know where to point it when you're done here. And what's more, the materials you put in its way must work not only for this ray of light, but for another one coming in here. So your design possibilities are very, very limited, and you would spend a lot of time worrying about whether you've got the right answer. Contrast that with transformation optics, which says the way we're going to design is to cut a little hole in space, and we're going to compress space. Einstein lets us do that, and push all of space out of that circle. So the space is compressed into, we're going to limit where we're going to put all this space that we're pulling out of here, and we put it inside this thing which we call the cloak. And so as we push the space out, so the light ray moves out with it. And no light ray can enter this region here because all the space has been pushed out. This is a totally disconnected piece of the universe. And any ray of light coming here will be pushed out. But at the same time, if we don't fool around with space here outside the cloak, then the light is not changed. So you don't have to worry that the light's not changing here, whether it's changing or not, because you've only distorted the space inside here. And that's the recipe for a cloak. Here's a pretty picture of it showing some mathematics for the compression of the cloak. You can compress it in various ways. Here's the simplest one we tried for the very first cloak. And when you've done that, the light will flow like water. Here's a computer simulation done by Dave Schurig of light entering a cloak, flowing around the hidden space, and finally exiting on the right-hand side there. Now, the first cloak was made at Duke University by David Smith, my long-term collaborator, and his team. And it was a cloak for radar waves. And you can see that the metamaterial element is here. And you can see how by altering the structure from the outer to the inner ring, you make exactly the right gradient of the refractive index so that the cloak hides things from radar waves. But that's very old hat now. So 2006 that was published. So I'll move on to more recent work, which was actually done in Birmingham, home of two of the Nobel Prize winners at one time in the last 2 days, Jerome Fraser and David Thowless, who was at Birmingham for many years. Anyway, this is work by Zhuang Zhang, and he wanted to make a cloak which is a little different from the one we talked about. So what he wants to do is to, starting off with a mirror, which might be a ground plane like the Earth for radar waves, or it might be a real mirror. And he wants to make a little hiding place here in which he puts something, but if you view it from outside, he wants this structure here to look as though there's still just a flat mirror there, okay? So the way he does that is to take little columns of empty space and squash them vertically, each by the same fraction, and then he creates this little tent here, this little triangle of hidden space. And the material he creates here, actually you don't need a metamaterial, surprisingly, because this is anisotropically compressed. You actually make something which is a crystal of calcite. And if you put two crystals of calcite like that, you have made this mirror invisible. Here's a computer simulation of what would happen if you had that triangle without the cloak. And of course, if you put light in, then the triangle has two facets and they produce two beams instead of the one beam that you get from the mirror. But if you put the cloak in place, then you get back to one beam again, and it looks as though the mirror is flat. And they had a very neat way of showing that the cloak was working. So here's the alphabet. And if you look at the alphabet through a mirror with a kink in it, there's a bit of the alphabet missing. A, B, C, D, blah, 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 R, S, T, U. But then you view the alphabet through a mirror with a kink in it, but with a calcite cloak that's designed to flatten the mirror, and lo and behold, the rest of the alphabet reappears. This, by the way, they point out to me, is in glorious Technicolor, and the reason it still looks black and white, the point they were making was that the cloak works across the entire visible spectrum. You see a little bit of chromatic aberration there, but there's been some dispute about whether cloaks are broadband or not. So that's the grand challenge addressed, and I hope you can agree that the design technology is quite, in my view, beautiful in that it can solve a problem just like that without really doing any mathematics, which at first sight you might imagine would take a lot of computing power to do. And there are other problems it can address as well. So I want to do two things before I wind up. One is to show you some really surprising, wacky things that you think shouldn't really happen, and then to go on finally to more practical things, of things which has definitely happened, which are products which are being made with metamaterials. So the surprising things, one of them is this. So I did allude earlier to a negative refractive index. So one way of altering the refractive index we've heard about is to compress space. So if you squash the space, it becomes more refracting. And I'm going to make some negative refracting material by squashing space. So I've got to take a bit of space, and I've got to squash it. And it becomes more refracting as I squash it more. And if I squash it infinitely flat, it will be infinitely refracting. And you know from your math class, if you have a function that goes up to plus infinity, and you go a bit further, it comes out to be minus infinity and goes down to negative values the other side. And that's what's happening here. So I'm compressing this region of space. It goes up to plus infinity, and then I go through that infinity, and I made a piece of negative space here, but I've had to do something very, very strange. So I've had to turn space in on itself. And in making this negative space, I've actually been forced to make a piece of space which has three values to it. So this piece of space has three manifolds, this one, and this one. So that if you register that, let's just see one of the strange things that can happen with negative refraction. So this is what ordinary refraction does. The light comes this side of the normal, and here's Snell's law. So if this angle is this side, it's positive, but if it goes to the other side, it's negative. And that's negative refraction, a very simple application of Snell's law. And you might say, well, what's the big deal about this number being negative? We can even look at complex numbers. But I suggest to you that this connection with the topology again, of space means that it's really a very surprising thing, and we should look for some very, very curious effects connected with negative refraction. And the man who first pointed us in this direction was Victor Veselngo, who's still alive today, living in Moscow. And he said we should look at negative refraction, and it would be a very surprising region. Unfortunately, there are no naturally occurring negatively refracting materials, but you can make them using metamaterials, and that has been done. And here is a picture of what might happen if you have a piece of negative refracting material. So because you bend the light back towards the axis, you get a focus here, and by the way, another one here. And Veselngo knew that he could make a lens like this. But there's a different interpretation of that, because if you buy this bit of negative space, you think the light's doing that in going through this material, but the light thinks it's doing this. And so this point here is in fact passed not once, but 3 times. And if the light comes to a very fine focus here, it will here and here as well, because it's exactly the same point as far as the light is concerned. And that leads us on to another conclusion. Now, Veselngo knew about this focusing effect, but he used Snell's law to derive it, which is inexact. And therefore, the assumption at the time was that these foci were subject to Abbe's law. And Abbe said, you can't focus light to better than about half the wavelength. But this result was derived using Maxwell's equations. And so what I discovered in 2000 was that this lens, if you can build it exactly as we say, would produce a perfect focus with the focus unlimited by Abbe's law. And that created a huge furore at the time, and a lot of argument in the literature, people saying it was wrong because it contradicted so many things that have been taught in school, but eventually it's stood the test of time, and experiments have been done which confirm that negative refractive materials can focus much better than the wavelength of light. And we're exploiting that in all sorts of ways in nanotechnology now to harvest light to a very, very fine scale. One of the problems with light and molecules is that the molecule is very small, and if you can only focus light to about 1,000 times bigger than the molecule, then the interaction between them is very weak. So if you want to do single molecule sensitivity, you've somehow got to harvest the light down to the nanoscale. And we're building devices which can harvest light and push it down to the nanoscale and force it to interact with molecules with unprecedented intensity. And that's being exploited by many laboratories to develop sensing devices, non-linear devices, and so on. I don't have time to tell you about them here, but let's have a bit more fun with negative refraction. So one of the other surprising things is that if you have a pond full of negative refracting water here, and you do a bit of ray tracing, you find that an object which is inside the pond actually has an image outside. So if you had fish in your pond, it would be very nice to see them swimming about in the air above the pond because of negative refraction. What other sorts of silly things can we do with negative refraction? I mean, I think it's very important to have fun in science as well as to do very serious things like make money. So here's a bit more fun. So one thing you can do is, this lens is so perfect that the image it creates is the same size as the object. But you can force it to make magnified images by taking the lens and using transformated optics to bend it round until it has a curved surface. And curved surfaces can magnify. So here's this blue region here, between the green and the blue, is some negative refracting stuff. And I'm throwing some light at it. And the prediction of the theory is that all the light that hits the red circle should enter the green circle here. Let's do a bit of ray tracing. So yes, this one goes straight through. It does go through the green circle. This one has to refract on the way. a bit of negative refraction there, and some more as it goes into a positive refracting medium here, and the same out the other circle. So yes, it's doing the job. It's grabbing all these rays. Here we have a problem, because the theory says that this light, and if you think in terms of a ray picture, which is wrong, then this ray should be grabbed by this lens, even though it doesn't touch the lens, and stuffed in here. But how does it do that? And the answer is that transformation optics goes beyond the ray picture, and this is a situation that where the ray picture completely fails. And what's happening is that, well, to explain it, let me first say what would happen if the light were captured here. So it would go to the edge of the lens, round and back, and round and back. It will be locked in there, classically. And this is what we call a resonance. And if you have a particle going by a resonance, if somehow that particle has a tail on it, then it will excite that resonance. So this light going here, the ray picture really should be modified. It's not in very thin wires. It has little Gaussian tails on it, and these will tickle the resonance and eventually excite it. So if you switch the light on, yes, this is the bit we filled first, and then slowly light will leak into these and fill. And here's a computer simulation using Maxwell's equations, which shows light coming in from the left, being captured by the lens, and filling the entire in a region here. So what can we do with that? Well, I set my student Weisheng Wei to make shadows. If you work in nanotechnology and you have a nanoparticle and you shine light on that nanoparticle, it doesn't make a shadow, because if the particle is comparable to or less than the wavelength inside, then the light will just fold around it, and there'll be no shadow the other side because of diffraction effects. So the secret is to make that particle, even though it's very small, to appear very big. So what we do is to take a black particle, which on its own, or even though it's black, would not create a shadow. And then we wrap a lens around it, and that lens makes this inner region appear as though it's as big as this outer region here. And so what should happen is that from outside you see this magnified black thing, which is bigger than the black thing itself, but crucially also bigger than the lens, which is creating it. So here's the shadow, here's some radiation coming in. You can see its wavelength, which is comparable with the object, and it's creating this really big shadow here. And now, finally, having had some fun, we earn our keep by inventing things and making products. So here's Richard Syms' work, who's collaborating with MRI specialists. If you want to make an MRI scan of, say, the heart, the way to do it is to insert a wire in a vein in your leg and push a little coil up that vein until it reaches your heart. And there it has a little coil on the end and can pick up the very, very tiny magnetic signals that tell you the structure of the damaged heart. Unfortunately, there's also some very high-powered electrical signals around, and they can be picked up by this wire, and if it gets hot, there are problems. You have to be very, very careful. And so Richard thought it was a good idea, instead of taking this beautiful, tiny magnetic signal and turning it into electricity where it's vulnerable, instead, why not keep it as a magnetic signal? The only thing he has to do is to design a wire for magnetism. So instead of conducting electricity, this wire conducts magnetism, and it's made out of metamaterials. And here's a picture. It doesn't reveal much about the structure of it, but that's the gist of it. And the important thing is that, of course, it's a response to magnetism and not electricity. This wire doesn't get hot. And he's working with some scientists in Singapore to get that out into the public domain and form a company. Here's another application. So one thing about these metamaterials, at least that radar frequencies, they're very cheap. They're just circuit boards with bits of copper wires on them. Some people, if they want to be insulting, say all you've done is built a circuit board. Yes, that's one way of looking at it, but there are more intelligent ways. And another thing you can do with these circuits is to tune their properties dynamically by putting DC electric fields near them. And in this way, you can make something called a phased array antenna. So if you want to use your cell phone in the desert somewhere, you can't because there's no cell phone receiver close by. And instead, people use satellite communications, which typically are a dish, about 30 centimeters in diameter. And this dish has to move because it has to point at the satellite. And then you can communicate. The dish is heavy, it's expensive, and it takes quite a bit of power. It's about $10,000, I'm told, though I don't own one myself. You can make something called a phased array, which gets rid of the dish and is just a flat plate of metamaterial, which can be tuned so that effectively, although it's flat, points at this part of the sky or the other. So it's very light, it's cheap. I think they hope to retail it for about $2,000, and it can be plugged into the USB port of your laptop. Kymeta is now marketing this, and they've been capitalized, I think, by Bill Gates to about $50 million at the moment. And they also have a deal with Toyota, who wants to put one of these devices on the roof of every one of its cars so there can be real-time communication with the car all the time. A car was test-driven across America in March from I think Seattle to Washington as a demonstrator of this. And finally, Terahertz technology. Terahertz is important for these autonomous guided vehicles, for active cruise control. It's the radiation that strips you bare at the airport when they want to detect what you're carrying. Now, Federico Capasso is the man for Terahertz, and he designed something called the quantum cascade laser, which allows electrons to cascade down little steps, and at each step it gives out a bit of terahertz. And the problem is persuading that structure to give out lots of terahertz radiation. And it's very successful, but he's making it even more successful by using metamaterials to couple in and drag the radiation out of the electrons. So, to conclude, I hope I've shown you that we have quite a diverse set of topics here. We've touched the hem of the great man, Einstein, who's inspired us with the design technology. We have this new concept of metamaterials that enables us to do things which were impossible a few years ago. We've had a lot of fun and surprises in electromagnetism, which, although an old subject, still has things which surprise us and can create controversy. And also, hopefully, we're doing our bit for the economy as well. So thank you very much for your attention and for inviting me.